We're in chapter 7 of the digital circuit book, and we're going to finish off chapter 7 today. And the first thing we have to consider is binary coded decimal addition. All right, well, that seems like, yeah, I'm going to have to do that. So I got some binary coded decimal. So let's see, what is that? That's 276. I have 276.
Addition is 274.
And then I've got 988. So I'm going to take 276 and add it to 988. All right.
This was BCD?
Yeah, binary coded decimal, right? We're in 7.5 on page 274. I don't have any.
274.
No, binary coded
BCD.
decimal, you can go to 9.
Oh.
Yeah, binary coded decimal, you can go to 9. So 988. So I expect to have a 4 there, 1 to carry, a 6 there, 1 to carry, a 2 there, and a 1. So I'd expect that to be my answer when I got done. All right, so I add this together and I get 1101, which is invalid, and I get 1111, which is invalid, and I get 1011, which is invalid. So obviously that's not what I'm supposed to be doing, right? So that's pretty dumb. We won't do that. So I got 6 and I'm adding 8. 6 plus 8 is 14. So I put down a 4. And I carry 1 to the next place. Okay, because this is the tens place. Alright, so I've got 8 and I got 7 and I got another 1, so that's for 16. So that would be a 6. And I would carry the 1. And then I've got 2 and 9 for 11, plus 1 is 12. Okay, 12 would be a 2. So I write down a 2. I have 1 to carry, so I'd put down a 1. And now I have my binary coded decimal addition. Thank you very much, computer. And so basically I'm going to do the binary coded decimal math in base 10, carrying like I normally do, putting down the numbers as I normally do them. Okay, questions about that? And the only thing the author does is add, so that's all we're going to do. All right, so the next thing we have to deal with is digital circuits that are arithmetic circuits.
Wait, do those ones that carry over even factor in?
So what's the question?
Do those ones that carry over factor in?
Yeah. 7 and 1 is 8, plus another 8 is 16. That gives me a 6, carry the 1. You bet. Just like it did over here. 6 plus 8 is 4, carry the 1. 8, 7 and 1 is 16. 6, carry the 1. 1 and 9 is 10, plus 2 is 12. Yeah, so doing the same exact thing, only different.
I think you just got lucky.
That's one way to look at it. Notice that the author does not do binary coded decimal division, multiplication, or subtraction. Yes. Isn't that cool? But he calls it arithmetic. Yeah. And he has rules we could go over, but they're sort of silly, so we're not going to do that. So where were we? What were we doing? Anybody remember? There we go. Put that guy up there. Okay, now we're circuits. So first thing we have is a basic adder. So we have an A and a B, which we're adding, and we can have a summation, and we can have a carry. 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1. So that's my basic adder. We also call it a half adder. And remember that, what's multiplication? Anybody know what multiplication is?
Just like adding a number to itself.
Yeah, so if we have 4 times 3, that's the same as 4 plus 4 answer plus 4 final answer. Right? So, and division's the same way. So division is just successive subtraction. And on Thursday we said that in 2's complement math, we don't need to subtract. We just add the negative number to the positive number, and that's the same as subtracting. So addition, multiplication, subtraction, and division are all the same operation. It's just that how we're accomplishing it by adding over and over again, if I'm going to do multiplication, or by subtracting over and over again if I'm going to do subtraction, if I'm going to do division. So in my calculator, all I need to do is know how to add, and then I can do everything else. Okay. Now I'm still hosed. I have to do sines and cosines somehow, right? So, but in general, the multiplication, addition, division, subtraction can all be done by adding. So that's the bottom line. So we have this half adder. So we're going to go and take A, and we're going to take B, and we're going to go and do an exclusive OR, and we're going to get to summation. And we're going to take A, and we're going to take B, and we're going to do an and we're going to get the carry. And that's the way we're going to do it. And that's is right here. I got 0, 1, 1, 0. I get ones. I get a carry. Carry out. But in the half adder, there's no, something's wrong here. Summation 0, right? There we go. That's better. Somebody should have told me about that. All right. Now, if we have a half adder, that means we have to have a full adder too, right? Full adder. So in a full adder, we're going to have some A, some B, some carry in, and we're going to have a summation, and we're going to have some carry out. Okay, so we look at that and we say, okay, what would that look like? 0, 0, 0, 0, 0, 0, 0, 1, 1, 0.
Is this the one you did yesterday?
No, Thursday, yeah. 0, 1, 0, 1, 0. 0, 1, 1, 0, 1. And 1, 0, 0, 1, 0. I'm getting there. 1, 0, 1, 0, 1. 1, 1, 0, 0, 1. 1, 1, 1, 1, 1. So now I got a truth table for a full adder, and then I have to come up with some way to make the full adder. And if I go and I go A, B, A, B, A, B, yeah. A, B carry in, and I do an exclusive OR on the A and B, and then I do an exclusive OR on the carry in with the A and B. I come up with what the summation is. That was pretty bad, wasn't it? All right, so this is A exclusive OR B, and then the summation is going to be A exclusive or B exclusive or C in. Alright, so what do we got? We got A not B or B not C, B not, A B not, A B not exclusive or with CN. Alright, so I've got A not B or B A B not C in knotted, or A not B or A B not knotted C in. A not B C not in, or A B not C not in, or A not B not C in, or A B C in. So I recognize this as an exclusive NOR, and that's why I can write it as an exclusive. I can skip steps between there and here to get there. But if I didn't recognize it as an exclusive NOR, it would be A not, or B not, and A not or B not. And that would be A or B, A not A, which is 0, and that'd be A B or A naught B naught, and then B naught with B would just be 0. So I skipped that step because I recognize that as an exclusive NOR. Well, now the issue is this really the summation that we had up here? And so I look back up here and I need a 1 at A naught B naught C in. A naught B naught C in, check. I need a 1 at A B naught C in naught. A B naught C in naught, check. So is that the right one? Yes. And then I need another one at A B naught C naught in A B naught C. That's this one. A B naught C naught in.
A was not.
A naught B. A naught B C naught. That'd be that one. And then the fourth one comes at A B C in. So I have the right summation, and so I have the right circuit. And then I need to carry out. So I need another circuit for my carry out. Now, because I can put thousands of these chips on the same piece of real estate, it doesn't really matter that it takes this much. So I've got A. We just call it A. We don't have to put a 1 there. There's only an A. An A, a B, a C in, a B, A C in, B C in. And if I AND those, and I AND those, and I AND those, that's an AND. And then I send them all through an OR. I end up with A, B, or A, C, N, or B, C, N. And I look back and I say, that's my carry out. And I go up and look at my carry out. And there's a B, C, N. B, C, in. Oh well, can't have everything. I misspelled CN. CN. No, BCN. And then I need another one at carry out at ACN. ACN, so there's ACN. And then I need another one at AB. And I get both those ABs happen right there, and it doesn't matter what CN is. I get a 1. So that counts for 2 of them. So now my carry out is something that that works too, and I've got that. So now I can turn the page and find that I can make these circuits in a different way, having the same type of thing, and I can do other weird stuff on it. All right. So now I decide that I'm sick and tired of being sick and tired, and I don't have to go and write all these AND gates and everything. I can go and say I've got a half adder, and I've got an A, and I got a B, and I've got a summation, and I have a C out. And I don't really care what's in the box, how you did it. I just have one, and I can have a full adder. And I can have an A, and I can have a B, and I can have a CN, and I can have a summation, and I can have a C out. And now I don't worry so much about how I made the half adder or how I made the full adder. I just say I have it, which is perfectly okay. So now I decide that I want to have 4 bits, and I'm going to do a full adder with the 4 bits. All right, so I've got A, the most significant A, the most significant B, a middle A, a middle B. That's a 3. That's a 2. A1, B1, A0, B0. So I got 4 bits of A and 4 bits of B, and I come into my full adder. I'm going to have a half adder first. So I got a half adder, and I get a summation. And we'll call it summation 0. And I've got a carry. I'm going to bring the carry over to a full adder. Bring the carry into the full adder, my A and my B. I get a summation 1. I get a carry. And I send the carry over to another full adder, and I bring in my A and my B. I get a summation 2, and I get a carry, and I send that over to the next guy. And again, when I'm doing this in integrated circuits, I have plenty of room to do it and plenty of architect to do it, and I can make it as small as I want. And I have a summation 3, and I have a carry out. So now I've got a chip that I can have 4-bit adders on, and I don't have to do it separately. 7483 is a 4-bit adder. And there's 3 more here that are 2 other ones that are CMOS that we won't care about. So now I'm looking on page 289, and I see I have my 4-bit adder, and it's sitting there. And it has a carry in now, so now I have to have full adders across the board. And I have a fast looking carry out circuit. So I don't have to wait for the carry to promulgate through the adder. I can go and calculate it first and have it calculated at the same time everything else is being calculated. Yes?
What the hell are you talking about?
I'm on page
Man,
280.
so
I'm on page 282.
282?
Yeah, I'm on page
Oh,
282.
I was on 281.
Yeah.
Okay.
So on the top of 281, I've got a 4-bit
Yep, I went to that.
4-bit adder. I have a carry in, but I'm calculating the carry out In the circuit I made up here, my carry out is being promulgated. I have to, in order to get the carry out, I have to wait for the carries to come from each of the individual guys. But I can calculate the carry out differently and have it calculated separately, and I don't have to wait for it. So on the bottom of page
Is this?
283, I see a carry out circuit that's bringing things in that are going to give me my carry out right away. And that's going to speed up the process. Not, we're talking about nanoseconds, right? We're not talking about milliseconds or microseconds. We're talking about this adder is going to add and give me the answer in 10 nanoseconds.
So you turn
Or less.
this four into a single chip.
Yeah, we're going to put it all on a single chip and have pin 14 be power and pin 7 be ground and use a single chip. That's what we're going to do. And on page 283 on the top, we see how we're going to use that chip in a circuit. We're going to go and say, okay, I got A1, A2 up to B, A4, B4. I got to carry in, I got to carry out, and I have summations across the board, and I'm going to get those things. And I'm pretty sure in your lab you're going to do something like that. Okay, on page 287, two complement adder subtractor circuits. So now I'm not going to talk about them. We're just going to, I think, pretty. And in your lab, you're going to build them. But I'm either going to add or subtract depending on whether or not the multiple exclusive OR gates have a 1 or a 0 going into them. So it's a 8-bit 2's complement adder subtractor on the page of 288. And then comes the cool things, the binary coded decimal adders.
Yes.
And we look at them and we say, well, isn't this wonderful? We're gonna take binary coded decimal and we're gonna remember where everything is, and we're gonna add them together. Yeah. So let's hope we don't have to do that very often. And in general, we don't. But our calculator's doing it all the time, and there's no doubt about it that we can't do it in our calculator. Then on page, turn the page. There we go. 291, 292. Page 292, we decide, it really is boring having inverters and having ands and having ORs and having exclusive ORs and things like that. That's just the most boringest thing. Why don't we just go and make some chip and then it'll do all those things for us. So, if we want an inverter, we're going to have selection guys, S0, S1, S2, S3. And if we have S0, S1, S2, S3, if we have zeros on each of those, then my output is going to just be an inverter. I'm going to invert the A signal. And so here's my A signal up here. So my A is 1001, and I do a 0, 0, 0. This becomes an inverter. I get A naught, which is going to be 0, 1, 1, 0. Okay. And or what if I just want to do a NOR? Yeah, if I want to do a NOR. So 0, 0, 0, 1. Now my output becomes A or B knotted. And but A is 4 bits and B is 4 bits. But it doesn't matter. I can set it as 0, 0, 1 and then just do a 1-bit thing. So I can do a NOR, I can do an A naught B, I can turn everything to 0. I can do an A or B, I can do all kinds of things. So, and I can have them be logical functions, or I can have them be arithmetic functions. So I've got a thing here, mode control. So I've got an M mode control guy here, and I can have it be logical, or I can have it be arithmetic. So if it's arithmetic and I'm at 0, 0, 0, 0 on my selection switches, then my output's going to be A. If it's logical, then I'm going to get A naught. If it's logical and I'm 0, 0, 0, 1, I'm logical, LOG, I'm going to get A or B naughted. But if I'm arithmetic, I'm going to get A and B, and I'm going to add them together. This isn't OR anymore. I'm going to add them together and get A and B coming out. So now this becomes a full adder, or a half adder. I guess it becomes a half adder. So there's 16 different functions, 32 different functions that I can do, both logical and arithmetic stuff. And we can throw away the rest of our chips and just use one of them. And you'll be able to do that too, so that'll be fun. So on page 293, it shows that I've set up my my arithmetic logic unit to be a 4-bit adder. So if I go and make my selection S3, S2, S1, S0. If I allow them to be 0, 0, 0, 1, 0, 1, 1, 0, and I have my M, my mode to be 0, I now have a 4-bit adder that I'm operating with. Isn't that just peachy keen? Now you do have labs where you get to do that, so that's pretty cool. Then we can do it more complicatedly. We're not going to do that. And now we're to the place where we get to do homework, which means we get to be simple again. So your logic circuits, think about the logic circuit that's inside your computer at home. What is that? You know, that CPU. That's a pretty complicated thing there going on, right? Yeah. So, but there's a whole lot of simpler things that could be going on that we did before we got to that very complicated thing. Now we have that very complicated thing in your computer, and we write our English Comp 1 paper, and every time we misspell a word, it gets underlined in red, and every time we leave a sentence not done, it underwrites it in green, and then we do a word checker, and it checks all these things out for us, and now we're friggin' geniuses because our English Comp paper, there's no misspelled words in it. Didn't used to be that way. You know, when I was in college, my 10-page papers were handwritten. You know, I had a typewriter, and my grandfather gave me a typewriter, manual one, and for 4 years of college, I only did one lousy paper on this hand typewriter thingy. You know, now we can do English Comp 1, we can do a paper every week. We couldn't do that before. When I was in college, my English Comp 1 class, you do a half-page paper every other week and hope for the best. You know, hope the professor can actually read it, which you probably can't because your handwriting is so piss poor. Okay, back to what we're doing. Problem number 7.1. 7.1 seems to have an A. Okay, so what we're going to do is we're going to perform these additions. We're going to convert the decimal to binary and add them and compare the answers. Okay, so 6 and 3 is 9. Okay, and so 6 is that, and 3 is this, and 1 and 0 is 1, 1 and 0 is 0, 1 to carry, 0, 1 to carry, 1. Ooh, I got 9 in both places. I am just so wonderful. I got 8 and I got a 7, and 8 looks like that, and 7 looks like this, and I add 8 and 7 and I get 15, and I add them together, 1, 1, 1, 1. Oh, that looks like 15 to me. We'll go off to H. I think you guys can handle these, right? 196, 156. 2, 1 to carry 5, 1 to carry 3. Okay, 196. Take my calculator out, turn it on. 196. Second function, base, convert to binary. And so I got 1, 1, 0, 0, 0, 1, 0, 0. 1, 5, 6, convert to binary. And I got 1, 0, 0, 1, 1, 1, 0, 0. I add it, 0, 0, 0, 1 to carry, 0, 1 to carry, 0, 1 to carry, 1, 1, 0, 1 to carry. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. My calculator will do that. Okay, so 1, 0, 1, 1, 0, 0, 0, 0, 0. Second function, base, type, binary. Second function, base, change to decimal. Boom, boom. Oh, goody. The calculator said that this was 352. All right, 7-3. You guys get to do the rest of them. If you think that that's really bad, then skip half or something. Repeat 7-1 for the following multiplications. All right, so I got A. I got 7 times 3, 21. I have 7 times 3. 1 times 1 is 1, 1, 1. 1 times 1 is 1, 1, 1. 1, 1 to carry, 1, 1 to carry, 1, 1 to carry, 0, 1. Okay, so I got a 16, and I've got a 4, and a 2, and a 1 for 23. How did that happen? That 23? 16 and 4 is 20 and 2, that's 23. 7 times 3. All right. Somebody fell asleep somewhere. All right, let's see what's going on here. 1, 1, okay. 1, 0, and 1 is 0. 1 to carry. 1, 1 to carry. 0, 1. That's different than I had last time, right? 16 plus 4 plus 1 is 21. There we go. We got it right. Did the multiplication correct.
Why is 1, 1, 0, and then 1, 1, 1?
Well, 1 and 1 is not 0. 1 and 1 is 0, carry the 1. And now I have 1, 1, 1, which is going to be 1, carry the 1. So 1 and 0 is 1. 1 and 1 is 0, carry the 1. 1, 1 with a 1 that's a carry is a 1, carry the 1. So that 1 becomes a 1. 1 and 1 becomes 0, carry the 1, because it's 2, and that's what 1 carry the 1 means, that's 2. And then 1, 1 and 1 is 3, that'd be a 1, carry the 1. 1 and 1 is 0, carry the 1. Okay, good enough? Yeah. Think of it as decimal math where you only have zeros and 1. Yeah.
I have much more trouble with subtraction than I do with the addition. Getting the negative numbers is my problem.
Oh, so you want me to do back to 7-2? So I didn't assign it on purpose, and you want me to do it?
Or division or subtraction, you're going to do it either way, right?
Oh, I hope not. No, I don't do it. I don't do either one. All right.
I just
So we'll
wanted to
do-
understand how to get the negative numbers.
All right. So we'll do one more in here. We'll do H. All right. So we got 2, 5, 5, and 1, 2, 7, and we're multiplying. Oh, that looks like a pain in the rear end, doesn't it? All right. 7 times 5. 5, 3 to carry. 8, 3 to carry. 17. 2 times 5, 0. 1 to carry. 1. 1 to carry. 4, 5. 5, 5, 2. 5, 8, 5, 6, and 5 is what? 3. 1 to carry, 2, 1 to carry, 3. So that should be my number. 2, 5, 5 should be 1, 1, 1, 1, 1, 1, 1, shouldn't it? 2, 5, 5. Convert to binary. 1, 1, 1, 1. No, one more 1 than that. So it's got to be, it's 4 1s followed by 4 1s. All right. And 2, 2, 7, 2, 2, 7 would be 1, 1, 1, 1, 1, 1, 1, I think, right? 1, 2, 7.
Yeah.
Convert to binary. 20 years of knowing what numbers are. Do you know what 7 is in binary? Yeah, you know what 7 is in binary. Okay, do you know what 15 is in binary? All right, that's fine. Do you know what 31 is in binary?
So just one short.
So
of the next
it's
number.
one short of the next number. So 2, 5, 6 is the next number, and 1, 2, 8 is the next number. I recognize it as being 1 shy, so it's all 1s. All right, so back to what we're doing here. 1 times that. 1, 2, 3, 4, 5, 6, 7, 8. 1 times that. 1, 2, 3, 4, 5, 6, 7, 8. 1 times that. 1, 2, 3, 4, 5, 6, 7, 8. 1 times that. 1, 2, 3, 4, 5, 6, 7, 8. 1 times that. 1, 2, 3, 4, 5, 6, 7, 8. How many do I got?
I
1,
can see
2,
why this
3,
is so
4,
much less
5.
complicated.
1, 2, 3, 4, 5. I need 2 more. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so I got enough. Okay, so now I'm going to add it. I got a 1. I got a 0. I have 1 to carry. Okay, I got 4. 4 is a 0, and the 1 to carry is not this row, but the next row over. I got 1, 2, 3, 4. I got it
Why would you carry it to the next row?
because this is the 2's row from here, and I have a 4. It has to go to the next column. 1, 2, 3, 4. 0. 1 to carry in the 4's position, not there, but here. 1, 2, 3, 4, 5, 6. Okay, a 6 would be a 0, and I got to carry a 2, and I have to carry a 4. 1, 2, 3, 4, 5, 6, 7, 8. 8 would be a 0. The carry doesn't go there. The carry doesn't go there. The carry doesn't go there. The carry goes there, right? Because that's the 2's, the
No,
4's.
that was one too
No,
far.
that's 1 too far, right? 1 too far. Put it there. I'm going back and checking myself. Which one are we on? On this row. 1, 2, 3, 4, 5, 6, 7, 8 again. 0. Okay, that's the 2's carry, that's the 4's carry, that's the 8's carry. 1, 2, 3, 4, 5, 6, 7. A 1. We got a carry a 2 and a carry a 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 0. We don't carry 2, we don't carry 4, we carry an 8.
So you're going over a row, it's not like a 1 row, a 2 row, then a 4, it's 2, 4.
2, 4, 8, right.
There's no.
Yeah. From where I am, yeah.
Okay.
1, 2, 3, 4, 5, 6, 7. 1. I need to carry a 2 and carry a 4. 1, 2, 3, 4, 5. 1. And I have to carry a 4. 1, 2, 3, 4, 5. 1. And I have to carry a 4. 1, 2, 3. 1. I carry a 1. 1, 2, 3. 1, 1. All right, now how are we going to get that number into 3, 2, 3, 8, 5? Because we know that our calculator only is going to do 10 bits, right? So we're particularly hosed. But if we break these guys up in the units of 3 and call it a 1, call it a 0, a 2, a 7, and a 7, and we call that base 8. Okay, so we're going to put in our calculator 7, 7, 2, 0, 1, second function base, type, octal, second function base, change to decimal. Alright, and I get a 2, 3, 2. Now, 2, a 3, 2, 3, 8, 5, which is exactly what I got there. Now, clearly there's plenty of room to make an error, right? Yeah, plenty of room. Okay, so now the front row wants me to do a 7, 2 problem. Okay, so we're going to pick G just to have one. And we're going to have 109 minus 60. That's what we're going to do. Okay, so I got a 9. 6 from 10 is 4.
We don't use that.
I know, but one of your classmates, I won't mention any names, that happens to be in the front row, wants me to do a subtraction problem for him. Okay.
Just show me the difference between 9 and negative 9, 5 and negative 5, 4 and negative. Just show me the difference between the two
So-
numbers. You don't have to do
So
that.
we need a 109. That's what we need first. So 109, and we're going to change that into a binary number. All right. So I got 1, 1, 0, 1, 1, 0, 1. Okay, and then we're going to take 60, and we're going to change that into a binary number. So 60 becomes 1, 1, 1, 1, 0, 0. And there's going to be, I'm going to put a 0 in front of this guy, like that. And I'm going to put a 0 in front of this guy like that.
Okay, why do you put the 0 in front?
Because I'm going to 2's complement math, and I need that most significant bit to be negative, and it's not negative in the 109, so I have to put a 0 there. So that it's weighted to be a negative number in the most significant bit. So I have to put it there. All right, now that it's there, I'm going to do a 1's complement. 1, 0, 0, 0, 0, 1, 1. And then I'm going to add 1 to it to make it a 2's complement number.
To make it what?
0, 1 to carry, 0, 1, 0, 0, 0, 1. 1, 0, 0, 0, 0, 1, 0, 0. Oh, that's not right.
I think last time we had to do it in
One.
8 bits.
No, you can do it in as many bits as you want as long as the last one is right. But I don't have enough zeros here. Boom, 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 boom. 1, 2, 3. 1, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, what did I do wrong? 1, 2, 3, 4, 5, 6, 7. How did I go from 8? 1, 2, 3, 4, 5, 6, 7. Wait, I only got 7 there.
Yeah, up on the right, you have four
Okay.
zeros between
Yeah, that's the problem. Okay, I got the problem solved already. Good thing somebody asked this so I could get it right. I need another thing here because they have to be the same. So this guy's 1, 2, 3, 4, 5, 6, 7, 8, and that is the place that negative is. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I do a ones complement.
So you added
One.
2 zeros to the front.
Because I needed the same number of bits in both numbers, yes, exactly.
Then you add 1 to make it a complement.
0, 0, 0, 0, 1, 1, and then that's a ones complement. Now I'm going to add a 1. 1, 1, 0, 0, 0, 0, no. 1, 1, 0, 0, 0, 1, 0, 0. All right. Now, we're going to look at this guy for a moment. This is the 2's place. This is a unit. Unit 2, 4. 4, 8, 16, 32, 64. Wait a minute. Unit 2, 4, 8, 16, 32, 64, 64, 128. 128 is a negative number. Subtract 68 minus 60. So this number is representing minus 60 because the most significant bit is a negative number. All right. Now,
Yeah.
So,
Why isn't that friggin' 128 plus 68 plus 8?
where's the
Or
8?
124? Why isn't it those added?
That's
How
a
does it
4.
make-
This is a
how do you designate
4.
that it's negative?
It is. It's 2's complement math. The most significant bit is a negative number. And that happens because it's the 8th bit. That makes it a minus 128. Anyway, back to what we're doing over here.
so
1, 1, 0, 0, 0, 1, 0, 0.
So roll down real quick. So we put as many zeros in front as we need to have the same number of bits.
As the other number, whatever it might be,
Then
right?
Then we add 1, and then
We
the
complement
front
it.
number, the front number's negative.
We complement it.
Add 1 to complement it.
We complement it first. All the ones become zeros. All the zeros become ones. That's what complement means.
Or complement it.
But
And
Then we add 1.
But when you see it, how do you know it's negative? I mean, if I just
Well,
saw that number, I would add all
Your
numbers together.
calculator. Let's put a negative number in your calculator. Minus 52. Okay, so I'm putting a minus 52 in my calculator.
Adding 1 is
Second function, base, switch to binary. So minus 52 in your calculator comes up as 1, 1, 1, 1, 0, 0, no, minus 52, switch to binary. 1, 1, 0, 0.
And then you added the second complement, that's how you know it's negative.
I would know
And it's,
then.
yeah, and that's how you know. Or if somebody says this is second complement number, then that's how you know. Like, you have to know what the number is, because you're going through the F group.
Oh, I
So
get,
invert it by
I
one,
understand how to get the
and
negative.
that's how you, it's not.
How
just
do I know
by
it's a
looking at
negative
it.
when I see it?
You know it's a negative when you see it if it says this is two's complement math, then that's how you know.
It's always gonna say that. It's always
It'll
gonna
say that. Now, if it's just like on a piece of paper, you'll never know. And
Yeah,
you're right. But
that's
if you
my
know,
question.
or if you do this and make it two's complement, then that's how you know.
Anyway, back to what I'm doing here. So minus 52 on my calculator, I have 1, 2, 3, 4, 5, 6, 7, 8, 9,
I got the same thing
10
you got.
bits. Well, what am I doing 10-bit math for? Isn't 1, 1, 0, 0, 1, 1, 0, 0, that 8-bit, isn't that also minus 52? Is it not? This is minus 128, and then this is a 64, and that's a 8, 12.
You're just using two's complement for that to get less.
So this is 76. Subtract 76 from there. 2, 5, minus 52. So my calculator is giving me a 10-bit 2's complement number for minus 52, but the 16-bit minus 52 would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 1, 0, 0, 1, 1, 0, 0. So that's a 16-bit 2's complement representation of minus 52. I could have a 32-bit representation. All I do is keep on adding ones. Anyway, back to what I'm doing here. I'm going to add these guys together, and I'm going to get 49. That's what I'm going to do. 1 and 1 is 1.
Now I understand how you got it. I just
0, 1 to carry.
determined if it was negative.
0, 1 to carry. 1, 0, 1 to carry. 0, 1 to carry. And we throw away the carry. All right, so what I got? I got a 1, 2, 4, 8. I got a 16, and I got a 32, and I add them together, and I get 49. So that's how I subtract using 2's complement math. And that's why we don't put it there in the problem set, because it might confuse somebody. All right, now we're going to look at now we're going to look at 7, 7. 7, 7. A. Don't want to confuse anybody. All right, we want to convert the following 2's complement numbers to a decimal. All right, so I got 0, 0, 0, 1, 0, 1, 1, 0, and we want that to be a decimal. 16, 21. B. 0, 0, 0, 0, 1, 1, 1, 1, 15. Echo. 1, 1, 1, 0, 1, 1, 1, 0. All right, so this is the minus 128th place. This is a 64, a 32, a 8, a 4, and a 2. So I take 128, minus 64, minus 32, minus 8, minus 4, minus 2, 18. So this is a representation of minus 18. Now, if I take my calculator and add a couple ones to this guy, I'm going to add 2 ones to this guy, and I'm going to put in my calculator 1, 1, 1, 1, 1, 0, 1, 1, 1, 0. I'm going to tell my calculator that that number is binary. And then I'm going to ask my calculator to tell me what that number is in decimal. And my calculator is going to tell me that I have a syntax error. So I obviously did something wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I put too many things in it. All right. Anyway, my calculator will do that for me if I entered it right. Maybe. 1, 1. 1, 2, 3, 0, 1, 2, 3, 0. Second function, type, binary. Second function, base, error again. Second function, base,
Isn't 822?
convert.
That's right there.
Huh? What?
Isn't 822? I've been looking at that one this whole time, like trying to figure out how you got 21. I'm pretty sure it's 22.
Yeah, it probably is. Oh, negative 18. So my calculator did give me minus 18. So there's a 16. There's a 4 and a 2. 22. All right, you rather have me put 22 there? Yeah,
I just wanted
typical.
to make sure you weren't getting tricky on us.
Typical. Okay, we'll do H. I've got 1, 1, 1, 1, 1, 1, 1, 1, and the answer is minus 1.
Okay, I'm not even gonna talk.
Well, isn't
I'll
it?
tell you, give me beer.
Isn't it minus 1?
Man. Where's my
All
land?
right, we got minus 128,
Now, you know it's negative.
and we got a
Does it
64
say somewhere?
and a 30 because we're in 2's complement math. 16, 8, 4, 2, 1. So if I take 128, I subtract 64, I subtract 32, I subtract 16, I subtract 8, 4, 2, 1. Yep, negative 1. Yeah.
The other problem is there was a 0 there, so the 1 is significant to make it a negative 1.
Mm-hmm. Because we're doing 2's complement math. No other reason. Okay, 7-9. Well-
Wait, there's two negative numbers? Or just negative 128 is negative?
The first guy is negative. The most significant bit is weighted as a negative number in 2's complement math. That's absolutely correct. All right, so where were we? 7-9. Convert the following decimal numbers to 2's complement form and then do the operation. Okay. A. 5, 0, 0, 0, 0, 0, 1, 0, 1. 7, 0, 0, 0, 0, 0, 1, 1, 1. Do the operation. 0, 1 to carry. 0, 1 to carry. 1, 1 to carry, 1. Or 12. 5 plus 7 is 12. Okay, we're going to move down to H. We need minus 36.
This is two complements form, isn't there like a negative?
No, because this is a positive number. This is the spot that's weighted as negative, and it has a 0 in it. Yeah. All right, so we need negative 36, and we need negative 48. And when we get done adding them, we're going to have negative 84. That's what we're supposed to get. Okay, so how are we going to get negative 36? All right, so we'll write 36. 1, 2, there's 32. There's 36. That's the 8, the 16, the 32 place. We need, all right, we're gonna go in, we're gonna do a complement. All the 1s become 0s, all the 0s become 1. and then we're going to add 1, and we're going to get 0, 1 to carry, 0, 1 to carry, 1, 1, 1, 0, 1, 1. So this is minus 36. And then now we need minus 40, minus 48. Okay, so we got a 0, 0, we have a 32, and we have a 16. 0, 0, 0, 0. 32 and 16 is 48, right? We do a complement, 1, 1, 0, 0, 1, 1, 1, 1. We add 1, 1, 1 to carry, no, 0, 0, 1 to carry, 0, 1 to carry, 0, 1 to carry, 0, 1 to carry, 1, 0, 1, 1. So that's my minus 48 guy. So now we're going to take the minus 36, 1, 1, 0, 1, 1, 1, 0, 0, and the minus 48, 1, 1, 0, 1, 0, 0, 0, 0, and we're going to add them together, 0, 0, 1, 1, 0, 1 to carry 1, 0, 1 to carry 1, 0, 1 to carry 1, 1 left over that we throw away. And we're claiming that this number represents minus 84. That's our claim. All right, so this is the minus 128th place. The 64, I have a 32, 16, I have an 8, and a 4. Okay, so 128 minus 32 minus 8 minus 4 gives me a minus 84. And that's the way I do that. 712. I could do that differently. I could have my calculator give me the 10-bit representation of the 2's complement number. I could do that. I'm not going to. 712. And now I'm going to go A minus 4. A is 10, minus 4 is 6. 6. I'm going to do the C guy. 1B minus 0, 6. B is in 11. 6 minus 11 is 5. 1, 5. I'm going to do the H guy. 8, B, B, 0. Minus 4, A, C, 8. Okay. 8 from 0. I can't do that. I have to borrow 1. So I'm going to borrow 1, and I'm going to make this a A. 8 from 16 is 8. I can't subtract 12 from 10. I have to borrow 1, making this an A. So this is 1A. So that's 16 plus 10, 26, minus C, which is 12, 26, that's a 14. A 14 is a D. A from A is 0, 4 from 8 is 4. Okay, so we take our calculator and go 8, second function A, now it's a B, second function B, second function B, 0, second function, what type is it? It's hexadecimal, and I'm going to subtract 4, second function A, second function C, 8, second function base type hexadecimal. I'm going to do that subtraction. My calculator is going to give me the answer in decimal. Isn't that convenient? Second function base, convert to hexadecimal, and my calculator says the answer is 4, 0, echo 8. Oh, I don't believe it.
You put,
D-
your
D
second
is-
letter you use as an A instead of a B. That's what your mistake was.
No, it wasn't. No, the mistake was that the D is 13, and I wanted a 14, and no one corrected me. So that's supposed to be an E, not a D. Because 16, 26 minus 12 is 14. 14 is E. 13 is D. Oh, bummer. Hate it when that happens. All right, that was 12. Going to 15. Which of the following are cannot be a binary coded decimal? All right, so that looks like a reasonable thing to put on a test, right? 15. A, okay. B, no. Right. C, no. D, okay. E, no. F, okay. So I can't have 10, 11, 12, 13, 14, 15. These are invalid binary coded decimal. So if I have any of those, then it's wrong. It can't be that way. And so that's how I would do that. 16. Convert the following to binary coded decimals, add them, and then convert the result back to decimal. 116A. 8, 3. 8, 3. Oh. And 11, right? 0, 0, 0, 1, 0, 0, 0, 1.
1, 1, 0. Or 0, 1, 1.
11.
What's 17?
No, that's 11. It's binary coded decimal.
Oh, shit.
Binary coded decimal. 1, 1. Yeah, I got to do it like this in order to, I can't do it over here. That'd be totally bad. Yeah. All right, do it again. All right, B. 12, 16, 12, 0, 0, 0, 1, 0, 0, 1, 0, 16, 0, 0, 0, 1, 0, 1, 1, 0. 0, 0, carry the 1, 0, carry the 1, 1, 0, carry the 1, 1, 28. 28. All right. I got lucky. 16, 19. The circuit below is an attempt to build a half adder. Is it working right? And a similar questions will be on the next test, by the way. I have many circuits that are right and wrong, and that's just the way it is. So I got A, I got B, and they go into there, and they go into here, and they go down like that, and we said this is summation, and then we come over like this, and we say that that's the carry out. All right, So now we look at this, and this is, I got A or B. I got A, B. I got my summation is A, B, and A or B, which becomes what? Just AB.
AB plus A.
AB.
or-
Well, yeah, A, A, B, or A, B, B, which would be AB, or AB, which is AB, also known as wrong, right? Because the summation is supposed to be A exclusive or B, and it's not. So the summation guy is wrong, and we don't have to continue.
Is there supposed to be an inverter
Where?
on the end, on the first end, and then the order?
Oh, shit. Now you tell me. Now I almost had the problem done. Okay, so you want an inverter here, huh? Okay, so this is that, that's that, and the summation is A, B, knotted, A or B, which is a real bummer, you know that, don't you? A naught or B naught, A or B, which is A exclusive or B. We already know that. We've done that many times. So summation is right. Bummer. Now we got to get the other guy. All right, so now we got carry out. It's going to be A or B, A, B knotted, A or B, the whole thing knotted. Isn't that special? All right, so I've got A or B knotted and A, B double knotted and A or B knotted. Okay, so I've got A knot, B knot, or AB, which is also known as A exclusive or nor, exclusive nor, B, which is back to wrong. Because the carry out is supposed to be AB, and it's not. All right. So isn't that special? 1927. Oh, look at that. Figure below is a 4-bit 2-complement adder subtractor. We are attempting to subtract 7 from 3, but keep getting the wrong answer, 8. Each test node in the circuit is labeled. It is. With the logic state observed by the test probe. Find the 2 faults in the circuit. Okay, find the 2 faults in the circuit. Okay, so $7.27. I'm going to look at B1. B1 is supposed to be a 1. No, B1 is supposed to be a 0, it's a 0. A1 is supposed to be a 1, it's a 1. B2 is supposed to be a 0, and it's a 0. B2 is a 1, it's supposed to be a 1. B3 is supposed to be a 1, and it's a 0. So B3, wrong. A3 is okay. B4 is correct. A4 is correct. All right. Carry out. Carry out is irrelevant. So now the issue is we're supposed to get a 4, right? So that means summation 3 is wrong. And summation 4 is wrong. And what did it say to do? Find the two faults. Bummer. We only found one fault. Let's see. B1, B and A1. B1, wait a minute. B1, A1 should give us a 1. And it's not. So the second fault of summation 1 is wrong. Because I'm getting a 1 and a 0, I should get a 1 out of the summation.
Where is that? An A1 and B1, isn't it 1 and 1?
That's 1 and 0. No, say coming into the chip, I have a 1 and 0 at A1 and B1.
Yeah.
And that shouldn't give me a 0. Oh, wait a minute,
You have a
I
1
got
and
a-
1, don't you?
I've got a, that's right, I got a 1 and a 1, you're right. So a 1 and 1 gives me a 0, 1 and 1 gives me a 0, 1 and 1 gives me a 0.
The
Summation,
problem is with
summation
A3 and B3,
4.
A3 and B3, there's a 1 coming to A3 and 0 coming to B3, so it should be a 1, but the output is a 0.
A3 and B3. Okay, the problem is in summation 4
Yeah,
is where the problem is.
but shouldn't
Yeah.
the output for A3 and B3 be a 1?
Yeah, we already called that as being wrong. So B3 is wrong. A3 is supposed to be a 1. It's connected to 1, it's supposed to be a 1, that's not a problem. But B3 should be a 1 and it's not. And that's the problem. And then given that I have, not given the real A, B's, and C, A, B's, but given that I have the A, B's that I have in the chip, summation 4 is still wrong. Because summation 4 should be a 0 with a carry the 1. So if I look at it, what am I doing? I'm doing anyway, whatever it is I'm doing. All right, so I got two things wrong. Moving on. Echo 7-3. Echo 7-3. All right. We need multisim. Load the circuit 7-7. Load circuit 7-. Okay. File. Open. Desktop. I don't see it. You see it? I don't see it. But I know it's there. It's probably zipped. Problems. 9, 7, 7. Is that all we get? Shown above is our subcircuits. blah, 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 blah. Okay. All right. So these are 7403s, which are what? 4-bit adders. I think. Are they not?
They're full adders.
They're full adders, yeah. 74. Oh, threes. Yeah, 7403 is a full bit adder. Okay. The issue is that I want to add 37 to 22. Okay. 13. Oh, way to go. These pin numbers are different than the pin numbers I have. That is a bummer. 7483. All right. We're hoping. All right, get out of there. We're hoping that even though they're the wrong pin numbers, we're sort of hoping they're in the right order. Where's my plus sign? Get out of there. Okay, we're going to have a 0 carry in. We're going to go to carry out to carry in. We're going to take this guy to carry out. Okay, now 116. All right, what we're going to do, we're going to hook up everybody low. Low, low, low. And why do I have to do that? Otherwise they're going to float high. Okay, now we're hoping that this is the 5's the least significant bit. Notice that that's not what it's saying on page 283, but we're sort of hoping it is. We're going to turn it on. Yes, 5's the least significant bit. And so if we add 5 and 8, that should be a 1 and 1, giving us a 2. Why doesn't that give us a 2? Okay, so it's going A, B, 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 B is what it's doing. That's why it's not giving us a 2. Okay, so we come over here and we go A. That's the first least significant B. Is that guy. Turn it on. Why does that not look like a 2? Okay, be that way. Be that way. Display my pin configuration. Don't display my pin configuration. Thank you very much. Now I did it. What did I do? Well, if we can't figure out who's on first base, let's see. We'll bring this guy up. That's interesting. Okay. Least significant bit, least significant bit. Wow. All right, there's a piece of paper. A, B, A, B, A, B, A, B, A, B. 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 2, 2, 3, 3, 4, 4. That's all I need, right? 1, 1, 2, 2, 3, 3, 4, 4? No. 5. How many do I have? 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. All right, 5, 5, 6, 6, 7, 7, 8, 8. All right. Way to go, Doug. You really did blow that one. Okay, so it would appear that pin 1 is the A. What happened there? That pin 4 can be A1. Okay, so pin 4 is A1. And 15 is who? One, 2, 3, 4, 5, 6, 7. $15 seems to be pin 4 is on the other side. We'll call him A. Pin 15, we'll call him A3. And pin 14 we'll call B3, 14. And pin 12, I messed that one up too. and 12 is who? 4, 10, 14, 12. Okay, we'll let him be a 12 will be a 2. And 11 will be that. Oh, that's bad. Okay, I lost my train of thought. Anyway, well, that's what you'd have to do. You'd have to figure out what pin goes to where. Why don't we just do it differently? Why don't we go get a TTL chip, which is a 7483. And get another one that's a 7483. And we'll do a rotate on these guys. Am I on? I'm on, when you know it. And we'll do a rotate on these guys. Rotate that way. Excellent. That big enough for you? And then we want the indicating lights, so we'll go grab the indicating lights. And we'll put them on this side. Okay, now we're better off. There's the carry out. There's the least significant bit. There's the next bit. There's the next bit. There's the most significant bit. Thank you for going that way. This carry has to go to the carry in. So we'll go to the carry in. And he's going to go there. And there. Are these the same pin numbers we had on the other guy? There. And there. We need a DC ground. We need VCC. We need VCC to be someplace on the board. Otherwise, the chip doesn't have power, and we need a DC ground on the board someplace. Otherwise, the chip doesn't have power. Okay, so we have all that. Now we're ready to go, except we need two numbers. What are the numbers we need? We need to add 37. So I need a 32, no 16, no 8, 4, no 2, and a 1. And I need a 22, which would be a 16, no 8, a 16, and a 6. Okay. 1, 2, 3, 4, 5, 6, 7, 8. So that's what I'm looking at. I'm looking at 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1, 0, 1, 1. All right, so that's what we're going to do. And now, so hook up the zeros first. Zeros first. Okay, 37 is going to be my A guy. All right, so I've got a 0. I've got a 0. I've got a 1. And I've got a 0. And over here I got a 0. and I've got a 1, and I have a 0. Okay, and then I've got on the other side, I got get out of there. Right, so I got a 1 in there, and then these two guys that I have left over are both 1s. And it would be nice if they were in a different color than red. Okay, my B is the 22. So I need a 0. I need a 0. I need a 0. And I need a 1. And over here on the B, I need a 0. And I need a 1. And I need a 1. And I need a 0. Okay, 0, 1, 1, 0, okay? And my carry in, even though it says carry, it looks like it says carry out, but that really means carry in. I'm going to make that a 0. He went to there, there went, okay, so turn it on, boom. And that's what we see. So we see a 0, 0, 1, 1, 1, 0, 1, 1. Is that a 59? That's the issue. Is it a 59? And so that's a 32, a 16, an 8, and a 3 for 59. Yes, it is. Oh, yes, we did it. Oh, I hope not. Yeah. Okay, what we're going to do something weird here. We're going to change the color of the zeros. Change color. I change it to green. So now all the zeros are green, and then we're going to change the red guy, we're going to change him to blue. Stupid computer. I know. I understand what I did. But that's not what I wanted. The blue. Okay. So now all the blues are 1, and all the greens are 0, and all the reds are who cares because they're just the other guys hanging out. And I could do the same thing for a 75 minus, which one are we doing? Oh yeah, it was 67 plus 45. Repeat part A for a different guy. And let's look at 7E4. 7E4. Load circuit 78A. And do the math that it says to do. Okay, let's hope that that circuit is more logical than the last one we had. So this guy's off. And we're going to go 7, 8A. Oh yeah. Oh yeah. That's going to take forever. Okay, well, I guess we're done with that. You guys can do that on your own, no problem.
No, yeah.
You start at the beginning of the day. Make sure you have plenty of time. Way to go, author.